So I would like to tell you about our X-ray and Raman studies on solid-state lithium-sulfur batteries built around lithium borohydrate as solid-state electrolytes. So first, I would like to tell you about the motivation for the study. So efficient energy conversion and storage is crucial for development of systems that are based on renewable energy sources. And in Denmark, for example, a large amount of electricity comes from renewable energy sources, that is wind power, and we see a lot of development. So in 2008, approximately 20% of electricity came from wind power. Last year, it was 40%, and the government expects that by 2025, 50% of energy will come from renewable energy sources. And this poses a problem for grid operation because it is very difficult to match energy consumption and energy demand. So as you can see here, this is an example from 2008 of October evening. So you can see that energy consumption peaked around 6 o'clock because a lot of people come home and use electricity supplies. But the production of wind power actually peaked around midnight. But the production of energy started 3 hours before the prognosis. So that means that efficiently 700 megawatt had to be fed into grid, which is a problem because you cannot, if you have a high percentage of electricity coming from wind power, you cannot regulate that much of electricity. So it has to be stored somewhere or sold on a common market, or you just have to downregulate the production of electricity. So there is a need to store the electricity that is stored from wind power. And there are some projects that try to focus on using batteries for energy storage, and the lithium-ion batteries with the lowest specific energy density. And another challenge for lithium-ion batteries that are used for storage of electricity, that is the dendrite formation because of the liquid electrolyte. So our solution to the problem would be lithium-sulfur solid-state batteries built around solid electrolyte. So because we use solid electrolyte, that means that we can use metal lithium on the anode side. And we can achieve higher energy densities by stacking the batteries. And we use the sulfur on the cathode side. So we use lithium borohydrate as the electrolyte. It is a complex borohydrate. It is used for hydrogen storage. It has a high percent of hydrogen content, 18.5%. And it exists in two polymorphs. The one above 120 degrees Celsius is highly conductive, while the other one below is not conductive. So here you can see that if you have pure lithium borohydrate, then it has high lithium-ion conductivity at temperatures above 120 degrees. But below that, it has low conductivity. But it is possible to stabilize the high ionic conductivity at room temperature by doping lithium borohydrate in silica oxide or by using halides. As you can see in the picture, the halides, they have highest ionic conductivity, but the problem with using halides is that they're not stable at high voltages, about 3 volts. Then you can use nano-confinement lithium borohydrate in a mesoporous scaffold, but it's somewhat a difficult process. Or you can do a confinement of lithium borohydrate in silica oxide by ball milling, and this is what we did in our study. So there are some theories on the origin of high ionic conductivity in lithium borohydrate, and we believe that high ionic conductivity is due to the interface that is formed between silica oxide and lithium borohydrate, which could be due to interactions with silynyl groups on the silica side. So lithium-sulfur solid-state batteries with lithium borohydrate as the electrolyte. Here you can see that at the charge and discharge plateaus, that during the first two charge and discharge, we see the two plateaus, but later we only see one plateau. That's why we have a question of what kind of mechanism we have in our battery. whether we're actually forming the polysulfides similar to lithium-sulfur systems with liquid electrolyte. And that is why we did the studies XRD, Raman, and synchrotron studies to see what kind of species we're forming in our battery. Now talking on the cathode side, we use carbon and sulfur. We use the optimized composites using ball milling, sulfur melting, and we use PVDF as binder, and then we tape cast it on aluminum foil. So we have successfully built and cycled solid-state lithium-sulfur batteries as capillary cells of 1 millimeter in diameter. So you can see in the picture, they consist of stainless steel rods, then lithium metal on the anode side, then solid electrolyte that is powder that is pressed in the capillary cell, and carbon and sulfur as powder and then pressed with a stainless steel rod. So we performed tomographic measurements at PR5 imaging beamline at Petrify in Hamburg. And you can see the picture. This is the cell, and you can see clearly the solid electrolytes, lithium on the anode side, and carbon and sulfur on the cathode side. So when we perform the tomography, it is somewhat difficult because the contrast between solid electrolytes and sulfur is low, and as also we have a lot of green artifacts. But if you align them manually, you can see that there are some crystals forming during the discharge. And here you can see the results of our tomography. So on the left-hand side, you can see that there is a sample slide when we enhance the contrast. That you can see that this one is the second discharge, that they start to be forming some crystals, some sulfur crystals. And on the right-hand side, that you can see this is the reconstruction of a capillary, that you can see the formation of different crystals, which could be sulfur. And we know that this is sulfur because they have different absorption coefficients. So the sulfur and solid electrolyte. So here the solid electrolyte is left out, so what you see only comes from sulfur. So later we wanted to know what kind of the species that were actually formed during the discharge. And there are some studies where they study the formation of polysulfides in liquid electrolytes during discharge. So there are several characteristic regions where you can see at the end of your discharge if you form in your lithium sulfide, lithium-2s, or the radicals, which is a precursor to lithium-2s. So what we try to do, we try to discharge our battery in situ using the capillary cell design and then see what kind of species will be formed. So here you can see it's the Raman spectrum of sulfur. Blue shows you the pristine spectra, while the red one shows you the spectra at the end of discharge. You can see that there's a lot of background noise, and that is because the blue one is used directly on the sulfur material, while the red one is done through the capillary cell. So that's why you have a lot of background emissions, so that's why you have the fluorescence. And here you can see at the end of discharge, in the several characteristic regions, we didn't observe the formation of lithium-2s or the formation of sulfur-3. So that means that we do not observe the formation of lithium-2s. At the same time, we did the ex situ XRD in our cell. There you can clearly see that we actually formed lithium-2s at the end of our discharge. And with this, I'd like to conclude. So the X-ray microtomography showed the formation of structures at the cathode, which is sulfur particles, but we do not know yet what particles are those. And so when we did Raman spectroscopy, it's a work in progress, but so far we had no evidence of lithium-2 formation at the end of discharge. But at the same time, when we did the XRD measurement, we could see the formation of lithium-2s. And this could be, as it was shown in recent studies, that lithium-2s crystalline is not formed unless the cell is allowed to rest for some time. And with this, I would like to thank you for your attention.
Very nice. Do we have questions? We have time. Yes, I see two over there.
Have you measured the conductivity of the LiBH4?
Yes, we did.
What is it?
I do not know the number, but there was a number passed. I just don't know the number now.
Okay. So do you know the order of the magnitude?
It's 0.1, I think.
0.1? Okay, thank you.
I have a few but very short questions. First of all, what was the thickness of your solid electrolyte?
For the one that we use in the capillary cells,
Yeah.
it was 1 to 2 millimeters.
When you use, can you prepare your electrolyte as a pellet but thinner? And what is the pressure that you use?
I mean, it should be possible to do that, and the pressure that we apply is around 2 tons per centimeter.
Did you test the compatibility with lithium of your electrolyte?
Yes, we did. It is stable against lithium metal.
Okay, thank you.
And there's another question here.
Are you planning to use neutron diffraction for to complement your results?
Yes, we did. It's just some work that's in progress, but we did that.
So you can actually guess in a better way about the lithium concentration on your sulfur particles?
Yes, we did that, but there's just some work that we're working on right now.
Okay. So, thank you.
Another question? Here's one.
Which excitation wavelength did you use for the Raman?
785.
And more? Did I see another hand? No. Okay, thank you very much. So